Thank you very much, Derek, for the kind words. It's my pleasure to be here. Actually, I was born in Maastricht, which people say is the most central point in this map, so it's here. So I'm exactly in the middle of the inter-region, so I'm probably the most suited person to give this talk. So I want today tell you a little bit about how solar cells work. And I divided it in 4 pieces. In the first part, I will give you a bit of a general background on transport in organic semiconductors. And then in the second part, we will talk about solar cells, not necessarily organic. So how do you make current in a semiconductor with light? And then the last 2 parts are then really specific on the organic solar cell, the Bullock heterojunction cell, where we see if we can apply what we learned here to understand something of the organic solar cell. So this is from a very old paper that indeed I worked on when I was working at Philips. And what we did here, we made a device with on one side P dot or ITO, which is a good contact for holes. On the other side gold. And the film was made from MDMO PPV, which is very famous from the group of Derek here in Hasselt. And what you do with this device is that when you apply a voltage, you inject holes. And in this way, you can investigate the transport of holes in PPV. Because if you use gold, you cannot inject electrons. So because of this energy offset. So it does not emit light, this device. It's a device that where only holes flow. So when you do this experiment and you measure the current, and you put it on a log-log plot, the voltage and the current, you see here, for example, this is a 700 nanometers device. You see a very nice straight line. And that has, when you look more carefully, has a slope of 2. And you remember probably from high school mathematics that a log-log plot, that a slope means that you have a power law. And in this case, a quadratic one. And you also see we tried this for different thicknesses. And then you look in a textbook, what can be, what is quadratic, and then you find this equation. It's called space charge limited current. I will explain in a moment what it means. But what is nice actually about it is that when you fit this equation, so here the red lines, to the measurements, that it has 2 parameters, the dielectric constant, and that is something you can easily measure. That's, for example, for this PPV in between 2.5 and 3. And you have the mobility of the carriers, and that's a very important number. That tells something about how fast carriers can move. So that means when you know epsilon, you have only one unknown parameter, and you get directly the mobility from the IV curve. And the number that we found back then was this number, 5 times 10 minus 7. And as far as I know, it was one of the first times that mobilities in such a diode were really reported. But if you look at this number, if you take this for silicon, the number is about 1,000. So that means that in a polymer, like PPV, MDMO PPV, that the current, the mobility, the carriers, they move something like 10 to the 9th slower than in silicon. So if I would make a processor from MDMO PPV, it would not run on a gigahertz, but on 1 hertz, roughly. So that's not suited for. Now, what does that mean? Basically, what it means is you start with a polymer that is undoped, has no charge carriers. Then you inject carriers from the contact into the polymer. So there is no counter charge, so that means that your device starts to charge up like a capacitor. And the amount of charges that you inject is given basically by the capacitance times the voltage. So the amount of carriers in the sample is proportional to the voltage. Then, of course, what you also have, if you have a current, you also apply an electric field. And the mobility times the electric field, that's the velocity of the carriers. So if you look at this expression, the current is something like the amount of charge carriers multiplied by how fast they move. And what you see now is that both are proportional to the voltage. And that's why you get a quadratic dependence, V squared. So if you would do if you look a little bit more in the calculation of this equation, you can also, for example, calculate how the electric field in such a diode looks like. And then what you see is that at the contact where you start injecting, in this case the holes, the electric field is very small, close to 0. But then it goes up as a square root of the distance. And for the carrier density, it's the other way around. It's very high at the contact, and then goes down with 1 over the square root of the distance. So in such a diode, such a hole-only diode, you have a carrier density that goes like this, and an electric field that goes like this. Now, maybe one extra remark. Of course, it can also happen that a semiconductor has already charge carriers, that it is doped. And in this case, like in this cartoon, this semiconductor here has a background concentration. It's called P0. So if I now apply a small voltage, then I get here this 1 over square root of x of my injected carriers. But as you can see, because the voltage is low, also the amount of carriers that I inject is low. And almost everywhere in the sample, the background density is higher than the carriers that I inject from the contact. So that means, basically, that the carrier density is a constant. And then I get Ohm's law. I get this equation. And that's just where then the current is just a constant carrier density multiplied by the electric field. So this is where Ohm's law comes from. That means that you have charge carriers in your sample, and that does not change when you apply a voltage. But of course, what happens if I now increase the voltage? I will inject more and more carriers, and at some point, I reach such a high voltage that the amount of carriers that I inject is everywhere higher than the background. And now these carriers dominate the current, and then I change to the quadratic equation. So what you will see in an experiment like this is that you start with a small ohmic regime, and then you get a switch to the quadratic regime. But as I said, if I take a metal, then P0 is so large that I will never reach the quadratic regime. It's always linear. Before I would reach the quadratic regime, the sample would have burned down already. So this means this cross point depends on how many carriers you have. In the polymers, this number is extremely low, and therefore I see from the start directly the quadratic equation. You hardly see the linear one. Now about this mobility number, as I said, it's like 9 orders of magnitude lower than silicon. And one of the main reasons is, it's probably often mentioned before, is disorder. And this is again a cartoon. So these are the PPV polymer chains. And now in the cartoon, what you see is that the conjugation is broken on many spots, and that you have basically conjugated segments. And if you want to have transport, like holes, they have to hop from one conjugated segment to the other. And that is a process that is slow. That depends, for example, on the distance between these segments and also on the difference in energy. And a popular model that has been pioneered by Heinz Bessler in the 80s and the early 90s is that if you look at this system, if you, for example, have a long conjugated chain, then the HOMO-LUMO gap is smaller than when you have a very short conjugated part. That's the quantum size effect. So then you can say that this polymer does not have one HOMO and one LUMO, but there is a distribution of HOMO and LUMO levels, depending on the environment and the length of a conjugated segment. And what will happen now, for example, here, if I look at the LUMO, if I would, for example, inject an electron, then the electron would, for example, go here on a side, but then it would search in energy for the sides and the longer ones that are lower in energy. It will relax in this density of states. If you now repeat the same measurement, but now you take a thin film, like 100 nanometers, and you go to low temperatures and higher voltages, then you see that in the beginning, the IV current is that's the dashed line here, is quadratic. But at some point, you see that the current goes faster than quadratic. So the quadratic part, you only see at low electric fields. That was one of the reasons why I showed you a measurement of a 700 nanometer thick film. Now, of course, the question was, what is happening here that the current now suddenly goes faster than quadratic? Because if you look at it in this equation, this one, that's basically only one parameter, and that's the mobility. So that basically means that the mobility must change somehow. Well, that took us quite some time, but what we did here is we combined, we determined the measurement in an LED, in a hole-only structure. So you see here again, sorry, this is a different unit. It's in meters squared per volt second, but you see here 5 times 10 minus 11, that's 5 times 10 minus 7 in centimeters squared. And here you see the mobility determined in a transistor. But if you now, so this is basically here we vary the gate voltage, so we change the carrier density, and we calculated at each point, at each voltage, what the carrier density was and what the mobility is. And then you see that these measurements fit nicely together, and that the mobility in a conjugated polymer depends very strongly on the carrier density, so on the amount of carriers that you inject. And so that also means that you cannot really speak about the mobility of the polymer, because that depends on which carrier density you measure it. Now what is happening here is basically the following. As I said, this is, for example, the Gaussian density of states, for example, the LUMO. Now if you inject here an electron, it will relax to a state in the tail of the LUMO. And if you now want to have transport, what normally will happen is that the electron will jump to a level that is higher in energy. Of course, that costs energy, but the advantage is that these levels here, higher in energy, they are closer together because the density of states is bigger. And transport between levels that are close together is easy. So what the carriers do, they find a level that is kind of a compromise between the energy step and the distance between the sides. And if you, what happens now, if you now start to increase the carrier concentration, so now I spoke, for example, about one electron or a few, so the Fermi level is here. But if I now, in a transistor, apply a gate bias, and I just start to increase the Fermi level, at some point, the Fermi level will pass at the point where the carriers normally are. And that means that the Fermi level is now the new starting point for transport. And when I increase the density more, the Fermi level goes up, and that means that the energy step that you have to make becomes smaller and smaller, and then the transport gets better. So the reason why this mobility is increasing is because I'm filling up all the tail states of the density of states. And that means I have more carriers at a level where the distance between the sides is smaller, and therefore the transport gets better. So that's the physics behind it. So later on, we, together with the group of Peter Bobert in Eindhoven, we made a model where the mobility then indeed depends on the density and the temperature and also the electric field. And with this, you can basically nicely describe the current, the whole transport in such an LED. So, or in a conjugated polymer. And it's not only valid for NDMO PPV, but basically for all polymers. So you can do the same experiment when you use now other contacts, like barium or calcium or something like that. And with such a device, you measure the transport of electrons in a conjugated polymer. When you do that experiment, here you see as a reference the quadratic hole transport. And here you see, for the same thickness, here more or less you see the electron transport. So what you see is first that the electron current is like 4 orders of magnitude lower than the hole current. But secondly, that this current is not quadratic, like this one, but it's much steeper. So if you look at the slope on this log plot, it's something like v to the power 6. Now, you can again look in your textbook, and then you find directly the word trapping. And let me also give you a short introduction about that, what it means. So it means you have a level in the band gap, where an electron falls in and where it cannot escape anymore. So it's lost for the transport. Now, if you would have only one nice sharp energy level, you can calculate that the current would still be quadratic, but it would be reduced compared to the normal space-limited current by a certain factor theta, which depends then on the amount of traps and on how deep the trap is. But it would still be a quadratic current. However, what can happen is that you do not have one level, but that there is a certain distribution of trap levels. And one that is used a lot in the literature is, for example, when the when the traps are exponentially distributed in energy. That means that close to the, for example, the LUMO level or the conduction band, you have a lot of traps. Now when you go deeper in the band gap, the amount of traps decreases exponentially. And the way how the trap density decreases is then given by a parameter which is called the trap temperature. But if you multiply that by Boltzmann constant, it's basically a trap energy. So that number says something about the shape of this exponent, if it's a slow one or a very steep one. And if you do the mathematics, you can calculate the IV. That has been done already in the early 60s. And then you find here the voltage to the power something, where that something is basically this trap temperature over T plus 1. So to give you an example, here's a cartoon. So this is, for example, the HOMO and the LUMO of PPV, MDMO PPV. These would be then the traps in the band gap. This is the same equation. And if I would use this equation to fit my experiment, that's what I did here, the yellow lines, I would find for the trap temperature, for example, a number of 1500 Kelvin. And if you look on the equation, it would mean 1500 divided by 300 is 5. Plus 1 would give me a slope of v to the power 6. And the amount of traps that's here in the prefactor, that is a number something in the 10 to the 17 per cubic centimeter. So apparently in this polymer, the MDMO PPV that we measured here, we have an impurity in the band gap with this density in the 10 to the 17th regime. And that captures our electrons, and therefore we have a low electron current. So one other problem as a next step, what we had was, it's very nice if you have an equation like that, but if you look more carefully, you see that all the important parameters like the electron mobility and the amount of traps and so on, they are all in the prefactor of this equation. So that means that you cannot discriminate by fitting IV curves if the traps, for example, are deep or close to the LUMO or even part of the LUMO. With all these models, you can fit your experimental data. So how can you solve that? One way you can do that is that you say, well, this is PPV, this is the LUMO and the HOMO, and now I add a molecule, like this cobaltocene. And now in the ideal case, when this molecule has a HOMO that is close to the LUMO of the PPV, I can transfer an electron. And that's then comparable to N-type doping in semiconductors. It's kind of a charge transfer reaction, but people often call it N-type doping, although it's not completely correct. Now, the idea we had was the following. If this is the LUMO of PPV, and we take a dopant that is a little bit in the band gap, like this molecule, then if the traps are deep, then this dopant can give away the electron, and we can fill all the traps. And if the traps are shallow, we can only fill a little part of the traps. When the traps are even part of the LUMO, that is just a different tail or so, then we don't do anything with the dopant because then the energy of the dopant is wrong. Now, if you do this experiment, that was kind of interesting. So this is the electron current. Here we start to add doping, more doping, and then at some point it stops. We can add more doping, nothing happens. And the point where it stops is exactly equal to the one in red, which is the whole current. So what you see is that apparently we have this picture here. So what happens is the traps are deep. We add doping, we start filling them. At some point all the traps are filled, so they do not bother the transport anymore. But we cannot give extra electrons to the LUMO because there is still this energy offset. So the rest of the dopants that we add, they do not ionize. So that gives us the opportunity to measure a system with all the traps filled with electrons. So then we can really measure the transport properties of the LUMO. And here in this, on the right picture, you see, for example, that you see here the temperature scan of such a device with all the trap filled, compared with the temperature scan of a hole-only device of the same thickness. And you see that they're almost completely the same. So what we can experimentally prove here, that once the traps are out of the game, that electrons and holes in this PPV, that they are transported in exactly the same way. And also we know that the traps are deep, because, as I said, we know that we are in this situation, and this offset here was about 0.4 eV. And that means that the traps must be deeper than 0.5 eV. Well, this part I will skip a little bit. As I said, initially we used this exponential trap distribution, but later we switched to a Gaussian one. For the reason that the simple reason is that if the LUMO is a Gaussian due to broadening, then if you have a certain trap and it broadens, it will also be a Gaussian. That kind of makes more sense. But the problem was that the mathematics of such a problem is much more complicated, and that took us much longer to incorporate that in our device model. But you can do that, and when you do that, basically you can also nicely describe your transport of electrons in PPV. These are 3 different PPV derivatives, so MDMO PPV, MEH PPV, and then one which is a physics name, NRS PPV, that means non-redshifting PPV. I don't even know the official name, but I know it has, instead of an oxygen, it has a phenyl ring on this. It looks like super yellow almost. So, but as I said, this is not the chemistry name. So what you can find then is that, again, the concentration is in the 10 to the 17th regime, and the level is something like 0.6 to 0.7 eV below the LUMO. So what we then did, we said, okay, you know, we have nicely done this. We also look at other polymers that, for example, you use in solar cells, like PCPD-TBT, PF10-TBT, and so on. And here you just see some IV curves of electron currents of these polymers, different thicknesses, so you cannot completely compare the magnitude. But what you can look at is the slope. And you see this is the PPV that has a slope 6. This one is less steep, this one is less steep. And it becomes, so of course, what we then as a next step did, we also looked at the transport in PCBM of electrons. But if you do that experiment, so we made a device like this, we injected electrons in the PCBM. On the bottom we had P dot as a work function of around 5 eV. But since the HOMO of PCBM is at 6, you do not inject holes in this case. So this is also an electron-only device for PCBM. So this is a film, it's only PCBM and no Bullock heterojunction. And then you find again very nicely a quadratic IV curve, trap-free, and you get a mobility 10 minus 7, but now in meters squared. So if you compare this with the whole transport in the MDMO PPV, it's about 1,000 times better. So what is now interesting, if you look at the electron transport, so I showed you all these slopes, and you plot this slope for the different polymers and PCBM as a function of their LUMO position. So here you see MDMO PPV with a slope of 6. And what you basically see is when the LUMO of the polymers goes down in energy and you reach something like 3.8, from that moment all your electron transport is trap-free. But when the LUMO is higher, you see that the slope gets steeper and steeper and steeper. And of course what we did, I don't show that now, but from all these polymers we made electron-only devices, we measured them as a function of temperature and so on and so on. And the result was quite surprising, namely that in all these materials we find that you can basically describe them with one kind of trap, one kind of impurity, that is located around this energy, so about 3.6 below vacuum, and it has a density in the 10 to the 17th regime. I showed you before 5 times 10 to the 17th for PPV, but for every material that we looked at, we always find more or less the same number, and that is very strange. So that also see if you, for example, now take PCBM, that has a LUMO here at 3.8, that means that if this impurity is present, it's outside the band gap and it doesn't trap electrons anymore. And then the LUMO of the material is lower than the LUMO of this impurity. And of course the question is, what is this impurity? That's still something we don't completely know. But one of the possible candidates are, let's say, water or water-oxygen complexes that might be in the polymer. because we do not believe it's something really chemical, because it would never, you could never explain why all the materials have the same number of traps. But it's still a part, we are still looking into this. Now there's something else that we also looked on later. What we also noticed, we also did optical measurements, and we were interested in the exciton diffusion length. Because, as you know, in solar cells, when the exciton diffusion length is long, you can make big polymer domains, and the morphology is not so critical. But for all the PPV derivatives that we measured, we almost found always the same number, something like 6 nanometers. Now, we learned that in many polymers, that you have a number of impurities in something like 10 to the 17th. So now you can do a simple calculation. You can say, when this is about the number of impurities, electron traps, then I can calculate how far they are separated, which is something like 12 nanometers. So that means, if I now absorb a photon, and I make an exciton, on average it has to travel 6 nanometers to reach a trap, which is exactly the reported exciton diffusion coefficient. So we started to suspect that all these exciton diffusion length, sorry, not coefficient, length, that they are all dominated by the impurities in the polymers, and that they are not the real numbers. So in the organic solar cells, everybody kind of accepts that the exciton diffusion length is short, and everybody puts a lot of effort to get the morphology in such a way that all the exciton can find the interface, but nobody ever asks, why is it so short? And we say it's because of the impurities. I will show you one example now. This is a well-known polymer for solar cells, the PCPD-TBT. So what we did here, it's also in this graph, we first did hole and electron-only devices, and we determined the amount of traps, which was electron traps, which was 5 times 10 to the 17th. And then we did time-resolved luminescence. And what we did here, we added a tiny little amount, you can see here how little, of PCBM that quenches the excitons. And the basic idea is, when you know how many PCBM you have, then you know the distance between them. And if you then know how the decay time changes, you can calculate the exciton diffusion length from this, from such an experiment. The only, of course, what is important is that the PCBM will not form aggregates, because then it doesn't work. But you see that the concentrations we are using is very low. And this is then the experiment. You can, for example, measure in solution, you can measure the film, and you can measure the decay when you have a small amount of PCBM in it. Now, regarding the theory, the lifetime that you measure you expect that it will linearly depend on the concentration of PCBM quenchers. And if you look, 1 over the lifetime, so this is the decay rate. And indeed, these are the experimental data. One of the reasons, by the way, why we choose this polymer is that you can see that the decay is single exponential, and that makes the interpretation very easy. And then also this formula holds, and you can see indeed that you get a very nice linear relation between 1 over the decay time and the PCBM concentration. And from the slope of this line, you can directly determine the diffusion coefficient of excitons, which is this number. Now, you can say also what happens now if I already have quenchers in my material before I add PCBM. Then you can rewrite the equations a bit. But what comes out basically is if I would know the real exciton lifetime, which we take the one of a very diluted solution, and I measure the one of the film, then I can directly determine the amount of background quenchers. You can also look at it in a graphical way. So if this was the real lifetime, the one I measure in solution, so this was also the one I was supposed to measure in a film, but I don't do that, I measure this one. So then I can follow this line and I can see for which concentration I reach this number. Now it turns out, when you look on the number, it's this number. And from IV curves, we modeled 5 times 10 to the 17 for the electron traps. And from time-resolved measurements, has nothing to do with current. We find 6 times 10 to the 17th for exciton quenchers. That seems to be too much of a coincidence. So what you can even do when you know this, you can even predict the PL efficiency of the materials, because when you know how fast they run, the diffusion, the excitons, how fast they diffuse, and you know how the distance between the quenchers, you can predict how many will make it, will still luminesce. But the main message that I want to give you is that we believe that all the exciton diffusion lengths that have been reported in conjugated polymers are not the real numbers. And also, I also believe that when we can make the materials more pure without defects, that we can go to much larger numbers of exciton diffusion lengths, and also to much larger polymer domains, and maybe even bilayers. And so, but we will see. So now I change to the second part. So it's basically a very simple question. I have a semiconductor between 2 electrodes. It's not organic or inorganic, doesn't matter. I shine light on it, so I make carriers. And the question is now, how much current do I get? What is the photocurrent? Very basic question. Oh, I'm sorry for this, this great text. So for people working on solar cells, I would advise you to read this paper. It's from Goodman and Rose in Journal of Applied Physics in 1971. So they basically explain the basic theory of photoconduction in a semiconductor. Now it turns out that there are 2 important parameters. You see them. It's the so-called mean carrier drift length. It's written here. Sounds complicated, but it's not, if you look at it. So this is a length. And as I told you before, the mobility times the electric field, that is a velocity. And tau is the lifetime. So this is basically the distance that the charge carrier can travel as long as it lives, so before it recombines, for example, or before it falls in a trap. And the same for the holes. So this is a length that a carrier can run after you make it with light, and then it disappears. Something else it's maybe good to mention in the theory of Goodman and Rose, they say we have a semiconductor and we put 2 electrodes, the same ones, on each side. And because they have 2 the same electrodes, they do not have something like a built-in field in their sample. But we do a bit different. In a Bullock heterojunction, we use, for example, P dot and lithium fluoride. And we have already, because we use electrodes with different work functions, we have a built-in voltage. And if you want to compare the results of Goodman and Rose with the results of an organic solar cell, you basically have to correct for that. So you have to look what we call the effective voltage in the cell. So that you compare these 2 situations and not these 2. So you have to shift your data with the built-in voltage. Well, I will show you that later, what I mean. So again, the question, I have a sample, and now I apply a very small electric field. That means that the length that the electron and the hole can travel is very small, smaller than the sample thickness. And what kind of current do I get? And it's basically given by this equation here. So you see it's an ohmic current. And if you look at it again, G, that stands for generation of carriers, generation rate. So this G depends on the light intensity and on the absorption, how many photons you absorb. Now, if you look at the equation, mobility times field, that's the velocity, and then multiplied by the lifetime gives you this length. So basically what you see is that the current is simply the amount of carriers that you make per second multiplied by the length that they travel. So length per second, that's velocity, and carriers times velocity is current. It's another way of saying the same. So it's basically very simple. You create a certain amount of carriers, and that gives you an ohmic current. So that means you take a semiconductor, you shine light, and you measure the IV, and you get an ohmic current. Now, you can also have the situation, like in a polymer, that the electron and the hole transport is not the same. And in this case, in this typical example here, it was assumed that, for example, the hole mobility is very small, much smaller than the electron mobility. So we have slow holes and fast electrons. And in such a way that this typical length for the holes is still smaller than the sample thickness, but for the electrons it's bigger. That means that electrons can leave the sample without recombining. So what happens now is that in order to help the slow holes out of the sample, so close to this contact, the electric field will become bigger. And in order to slow down the fast electrons a bit, here the electric field will become lower. So that means that is the most important thing. In this semiconductor, the electric field is not anymore constant in the sample. So what it basically does, it adjusts itself in such a way that it will help the slow carriers, because the current as a function of distance is a constant, because otherwise carriers would just disappear. And if you, Goodman and Rose, they solve this, and what then comes out is that the current is now proportional to the voltage to the power half. And it's still proportional to G, which is, as I said, the light intensity, if you want, or the absorption. So what that means is, if you have such a semiconductor at low voltages, you will first get a linear relation. And then at some point, when the fast carrier can move the sample without being lost, without recombining, it will change from 1 into a slope half. Now I can go then to even higher voltages. Then I extract both holes and electrons without recombining. So that's the ideal solar cell, there's no loss. And then I get a constant current. So it doesn't matter if I make the voltage higher, the current doesn't change anymore. And of course the reason is that what happens here, so the current in this case is given by this number. So it's again the generation times the length, but this times the length is the sample thickness. And what it means is, if you basically, simply spoken, it means that the amount of electrons and holes that come out of the sample are equal to the amount of photons coming in that are being absorbed, because there is no loss. And of course you can increase the voltage, but the amount of photons coming in per second is a constant number. So the only thing that happens is, if a photon comes in and gets absorbed, and you make a very high field, you will extract the electron hole very fast, but you still have to wait for the next photon before the same happens. So the total rate is just determined by the amount of photons that come in. So that also means, if you can measure this, that you know directly how many carriers you have generated. And then there was at the end in their paper, Goodman and Rose, they made a special remark. They say, hypothetically, suppose you would have a semiconductor with an extremely low mobility, in such a way that the amount of carriers that pile up here becomes so big that you get a kind of electrostatic problem, electrostatic limit. Then they call that the space charge limited photocurrent. What happens then is that you get also a current that goes with the square root of the voltage, but now it's proportional to the light intensity to the power 3/4. A special case has never been observed, but that came out of the mathematics. So to summarize, you have a linear behavior in the beginning, then a square root behavior at intermediate voltages, a constant photocurrent at maximum voltages, and a special case for samples with an extremely low mobility. So now we switch to the organic solar cells. How much time do I still have before the break?
5 minutes.
5 minutes, okay. So this I don't have to explain, donor and acceptor, electron and hole. The only problem that is still a problem today is that that you make this bound state at the interface after the electron is transferred. And there is still a discussion how this state is, how you break it up. Because if you do a simple calculation when the electron and hole is separated by 1 nanometer, you have to overcome a binding energy of half a volt. But people still disagree about how this process exactly works. In many cases, the dissociation is more efficient than what you would expect on basis of this barrier. What we do now, we have a Bullock heterojunction with 2 phases, acceptor and donor, and now we make a very crude approximation. We say we consider this system as one semiconductor, where the conduction band is the LUMO of C60, and the valence band is the HOMO of the PPV. And then we are going to apply Goodman and Rose. But as I said before, we have to be a bit careful that because we use different contacts, we have to make this correction for the built-in voltage. So if you look here, if I now apply the built-in voltage, that's what I'm doing here, then I get a flat band, and that's the same as in the case of Goodman and Rose at 0 voltage. So I have to shift everything by this number. And what we also wanted, everybody knows this measurement, the dark current and the current under illumination, but we didn't like that because we wanted to see the photocurrent as a function of the electric field in the sample. And we know that close to VOC, that the electric field is very small. So V0 is that's where the difference, we look at the difference between photo and dark. I will not go into that now. But what we do basically, we change the normal measurement. We take this point as our new origin here. And then when we go like this, in our case we go like this. So this means 10 volts here means almost minus 10 in reverse. So we plot V0, it's this point minus V. So we rotate this picture by 180 degrees. And the reason why we do that is that now we have the current in the solar cell as a function of the electric field in the solar cell. And then we can compare it with Goodman and Rose. And what we see already is that the first part is indeed linear. And then we see a kind of bending off. But then the experiment, this would be the saturated one. But the experiment goes up here when you go. So what we do here, we put minus 10 volt on our solar cell. And we see that the current still keeps on increasing in reverse bias. This is, for example, a comparison between a silicon solar cell. You can see that's linear all the time and then indeed nicely saturates. And the organic solar cell, in this case the PPV, that is linear, then kind of bends, but then gets a kind of S-like shape. And only at very high voltages it reaches also, it starts to saturate. So, of course, this was in about 2003, 2004, when we were working on this. And we wanted to make a device model, a numerical simulator. And for people of you who have ever worked on that, what you typically do, you take a solar cell and you divide it in many points. And then in every point you calculate the electric field and the density, and you have to do that in a loop that converges. So that means we had to use a relatively simple model to calculate how many carriers we would make in an organic solar cell. And we used a model that is called the Brown model. What it basically says is you have the donor, you create an exciton, the exciton diffuses, you make this charge transfer state at the interface. And then there are 2 options. So the charge transfer state can recombine, or it can form and dissociate into free charge carriers. But what of course can also happen is that when you have electron and hole traveling to the electrodes, that they meet another electron or hole and they recombine again to make a bound pair. So these are the processes that we modeled. And there are some numbers in there, but what I want to state is that in order to calculate how an electron and hole separate in an electric field, we use the so-called Onsager model. But the important parameter in there is the distance between electrons and holes that you have when you start to separate them. The other ones I will not go into now. But here you see it's more interesting. You see a measurement. So this is a PPV PCBM cell, but now plotted in our way. So the current versus the electric field. And this is the linear part. But here we said when now this G, this generation rate, depends on the electric field, because when you have an electron and a hole and you try to separate them, when the bigger the electric field you apply, the easier it goes. And we use this Brown model to try to simulate that behavior, and you see that works quite well. But what is more interesting is, for example, if you only look at the experiment at minus 10 volt, you see that all the photocurrent saturates. They also becomes temperature independent. So that means that directly from the IV, we can determine how many carriers our blend absorbs. We can measure that directly from the current because we know the sample thickness. And what we can also see, for example, if you look, this solar cell has an open circuit voltage of 0.8 volt. And that means that the short circuit current is somewhere here. So that means that the short circuit current is about 60% of the total current. So that means under short circuit conditions for this solar cell, when we now apply a high electric field, we can separate the remaining 40%. And so without doing any calculation or anything, so we can tell how many carriers we absorb and how many are still sticking together at the open circuit point. And how many we can release when we apply a big field. And of course, what you want for a real solar cell is that this is, of course, flat. That you don't want this increase with field, because the solar cell only works in this area. So what we did, we incorporated this process in our device solver, and then we could nicely model the, you see, from open circuit all the way to minus 10 volt in reverse. We could model very nicely for different temperatures the photocurrent of these solar cells. And let me make one more remark about it. As I said, this model has two parameters. If you go back, one is this, how fast a bound pair recombines, and the other one is the distance between an electron and a hole. And because the model is too simple, these parameters are not the real numbers, but I do believe that they really give the right physics in the way that this is really an effect because of dissociation. But the real meaning of these parameters, that also contains the morphology and the interface structure and so on and so on. So it's like an effective number. So for our purpose, I think here it is sufficient to say that we kind of know why the curves look like this. So we still have to dissociate carriers. But the numbers, for example, the distance is something like 1.4 nanometers or 1.2, but that's not a real number. That's just because the model is simple. But so before the break, so what I want to say is if you take an organic solar cell, you put it in minus 10 volt, then you can determine exactly how many carriers it has absorbed. You can also look at short circuit current, how many carriers are not dissociated there. And as I said, with a simplified model, you can basically nicely describe the characteristics completely. But you just have to be careful that the two parameters in there, that you do not say that this is the real electron-hole separation and the real lifetime of the pair, because there are still a lot of things underneath, like the morphology. Then break. Yeah.
Okay.
Yeah.
Thank you.